All right, hello everyone. Welcome back to Historical Geology 1404. Today, let me get this off the camera so we don't have this weird inception thing going on with the camera inside a camera inside a camera. Well, today is lecture 7. We are continuing our discussion of evolution on Earth and correlating all of that to the rock record today. Let's talk first though. What happened this week that was of note, geologically or otherwise? Yes.
I saw on CBS News there was a geologist named Minnick Rosing. He was disproving claims that the U.S. thinks there's like minerals, like high rare minerals in Greenland, because they want to compete with China. But he's like dismissing those claims.
In Greenland? There are lots and lots of minerals in Greenland. As a matter of fact, I have a sample of a mineral in one of those drawers over there that can only be found in Greenland. It's the only location that we've ever found it is over there, and it has several uses. But yeah, I don't think that there are enough of the rare earth metals that we know about in Greenland to compete successfully with China, at least not without an incredible amount of investment. There are no obvious mining sites that we know about. But again, much of Greenland is covered in ice right now, impossible to survey. It is very possible, considering the size of Greenland, that there could be some very, very valuable metal deposits uncovered in the next few decades or century as that ice melts. I thought I heard someone talking over here. No? No one is gonna or something? All right. What else?
Oh, yeah, no, yeah, actually.
Okay, yeah, what?
The Masters.
The what?
The Masters was going on in the golf tournament.
A golf tournament. I know nothing about that. Fill me in.
Rory McIlroy won.
Rory McIlroy? That's a name. Rory McIlroy. My brother has a speech impediment, and that name would give him fits.
Pretty interesting.
Yeah. Cool. What else? We had some tariff drama go on this week, right? Oh, 150% was definitely what some countries got. Some got more, some got less. The Penguins got a nice tariff put on them, which was nice. They can keep all their goods for all I care. Unless it's eggs, they should give us all the eggs. Cambodia, for some reason, got hit with like a 93% tariff. I don't even know what we get from Cambodia outside of maybe some clothing. I can't recall looking at something and seeing made in Cambodia very often. But anyways. And most of them got lifted. Why?
We were hit with even harder tariffs in response.
There were definitely tariffs in response. Thank you, Mary. There were some tariffs in response. Wow, look at those shoes. Those are quite the thing. I've never seen, those are like high heel Crocs. Like
Yes.
those have got some crazy.
My right heel is killing me.
Okay.
I think I have like something fasciitis or
Oh,
something.
okay.
And
So
everybody kept telling me to get Crocs.
You're basically walking on marshmallows right
and I'm
now.
like, they're hideous. So I have
Hey, it gave you what?
jazz it up.
It looks like it's added 3 inches, right? It looks like 3 inches taller with those on. Okay, well, you must participate. I have kept my promise. There are 4 varieties of licorice.
Oh,
Go ahead and try them, and then tell me which one you like the most, and I'll put your vote up here on the board.
I didn't even know Twizzlers were a variety of licorice.
Huh?
I didn't know either.
Yeah, I didn't even know Twizzlers were a variety of
Yeah.
licorice.
I love Twizzlers.
Okay, well,
When you said licorice, I was thinking the ones that taste like cough medicine.
well, try them and see which ones you like. We're talking about tariffs right now. Mm-hmm. Yeah, so the tariffs were lifted after a couple of days. A lot of people do think that it is because of the rising cost of things, because of the tariffs that we got slammed with in response. That's very possible. I would say it's equally likely that Trump got ganged on ganged up on by a bunch of millionaires who said, hey, this is bad for business. So I don't know which one it was. Either way, tariffs. Most of the tariffs. China is still under tariffs. The only tariffs that he lifted on China, I believe, were for cell phones and computers. Every other tariff on China is still active as far as I'm aware. So buckle in, folks. It's going to get spendy. But this affects economies everywhere, in every country. The United States and China are central to almost every major economy in the world, right? Through the goods that we provide, the oil we produce, the labor that we have, right? So the food, in some cases, that is provided. So this is going to have some far-reaching effects. So it'll be interesting to watch how this develops as time goes on. Any other thoughts or notes on that, or anything else before we begin? You thinking about it, Alan?
I think I have one question.
Yeah.
What's the difference between a geologist and archaeologist?
A geologist and a what?
Archaeologist.
Archaeologist. Fantastic question. The difference between an archaeologist and a, well, paleontologist is the branch of geology that would come closest to that, is about 10,000 years. We tend to draw the line at 10,000 years. Anything more recent than 10,000 years, we will turn over to an archaeologist most of the time. Anything older than 10,000 years, they will turn over to a paleontologist most of the time, because that's about how long it takes for something to become fossilized. Now, there are some exceptions to that rule. Anything that is obviously correlated to the development of human civilization obviously would go to an archaeologist at some point, probably as a joint venture between the paleontologist that found it and the archaeologist. If an archaeologist finds evidence of a fish that we thought was extinct that's in the fossil record, but they're like, oh, wow, it's actually alive somehow in the midst of their travels or whatever, they will typically turn it over to biologists or paleontologists to figure it out because it's not their specialty, right? So there's some interplay there, but generally speaking, that dividing line is 10,000 years. Good question. Anything else? Cool. Let me make sure that this is actually recording, that we are rolling. I really hope that it's capturing audio. All right. Let's get cracking on this then. All right. So, correlation and dating of the rock record. We talked about this neat little tool called stratigraphy, right? You've all done this lab by now. Fingers crossed you have, right? This week I'm hoping to bust out a whole bunch of grading. I didn't get a whole lot done last week. I did some at the end of the week before. Last week was nuts. Today's going to be pretty nuts. I have a research project for my PhD to finish, so hopefully tomorrow I can bust out a bunch of grading. Okay? But yeah, please make sure you've got your labs turned in, and those of you online, please make sure that you're keeping up. So, stratigraphy. What's the point of stratigraphy? This allows us to do some neat correlation between layers of rock. But within one vertical sequence, say through a core sample, I can correlate this layer to that layer to that layer to that layer to piece together information about the history of that location through time. But I can also take a stratigraphic column from here and compare it to a stratigraphic column 100 miles away and see where the two layers or where multiple layers meet up. And then that allows me some interpretation for everything that happened in the 100 miles between those areas. Okay? This is correlation. But it didn't start. The practice of correlation didn't start in recent years. People actually learned fundamentals of how to correlate not only rocks but the fossils within them a long time ago. So we're gonna talk a little bit about those, I guess you could call them fathers of the fossil record studies, okay? I kind of group them into an overall category of curious and observant men. And there's also women, by the way. I just want to put that out there. There are plenty of women who have made incredible contributions to this field. Did you finish the licorice?
I did.
Okay, which one did you like the most?
The first one that was kind of darker.
Kind of darker and longer?
Yes, and it didn't any little stripes on it.
Okay, so it kind of looked like a tube, like a smooth tube. Look at that, guys. You all like Australian licorice. Yeah. So no one voted for Twizzlers. One person voted for Red Vines. And then 9 of y'all voted for the 2 different types of Australian licorice. This was the purple one. That was huckleberry Australian licorice. And this was strawberry Australian licorice from a different brand. So look at that. You all have different tastes now. No more Twizzlers for you. No more eating old wax. Right? Huh? No? All right. Cool. I love it. All right, so let's talk about these dudes. The first guy we're going to talk about is Nicholas Steno. He was alive from 1686 to 1636. Quick math, he died at 50, right? 50 was actually, back then, a ripe old age. Okay? Yeah, I know. They didn't have the healthcare we do now. Leeches and guys with bird masks, that's what it came down to, right? It's kind of dark, but oh well. All right, so he was Danish. He started off being pretty active in scientific fields, okay? It's actually from him that we start getting the beginnings of the first original horizontality. You guys remember the principle of original horizontality? Original horizontality. What does horizontal mean? You're all doing this. All right. Horizontal. That depends entirely on your frame of reference, right? From where we're standing right now, this means horizontal. This would mean vertical, right? So what is original horizontality as it relates to geology?
The layers.
What about the layers?
The lower something is, the older it is.
Oh, that's superposition. But I love where your mind is. It has to do with the layers. But what about the layers?
How they're parallel with its bedrock.
Well, bedrock can be what we're talking about here. So again, that's perception. Original horizontality states that all layers of rock, sedimentary rock at least, are deposited horizontally. That sediment has to be deposited horizontally. How easy is it to deposit sediments on a near vertical surface? Right? You can't. You can't here. That's difficult. That's possible, but originally horizontal or near horizontal, all layers of sedimentary rock must have been at one point for them to have been formed. If I find a sedimentary layer at that angle, I know it's been moved after the fact to that angle because sediment cannot be deposited on that kind of a slope, right? So that's original horizontality, all right? He also had some theories, some ideas about where fossils came from. I'm going to erase our Australian victory here real quick. Okay. Now, I mentioned that he started off as a scientist. He spent some time in the scientific fields, contributed to a couple of different sciences, including geology. He was, you remember that term naturalist, right? Naturalist is someone who studies the physical natural sciences kind of in general. So he contributed to biology and geology and physics and chemistry and astronomy and a little bit like that, right? I like to think of the naturalists as they couldn't choose their major, so they just did a little bit of everything, right? Except there wasn't really a major back then. Doing a little bit of everything was kind of the thing to do. So he actually ended up converting to, I believe it was Catholicism. Okay, he converted to some major Christian denomination and actually ended up leaving behind all of his scientific pursuits to become a clergyman, which, you know, good for him. He made his choice. Did what he wanted to do. Ain't nobody hold that against him, right? We all do the same thing one way or the other. But he did make some pretty cool contributions to geological sciences, including original horizontality. Then there's William Smith. William Smith is an English surveyor. Who can tell me what a surveyor is/does? Calls people and asks them stuff. Yes, that is what most surveyors are today. Would you like to take a survey? No. Right?
Don't they measure land? Like when you're buying property, they have to measure.
Yeah. That's the other definition of a surveyor. Okay? Someone who does land surveys. Are you ever driving down the highway and you see those guys in the bright yellow fluorescent suits that people can see them, right? And they've got this yellow tripod and they're looking through it, and another guy a mile further down the highway that you pass in a second, and he's got a weird camera thing looking back at that guy. Those are surveyors. They are mapping out, measuring exactly point to point for some project that is going to happen. A road expansion, an off-ramp for that highway, a building that needs to be constructed. Yes, the oil field uses a lot of those. Why? Because when an oil company goes to a ranch owner, let's say, and says, hey, we want to drill on your property for oil, then the ranch owner says, okay, you can have a 25-foot by 55-foot pad, right? And then that surveyor is going to go out there and be like, boom, boom, inch to inch, you do not step foot over that, right? Otherwise, you are in violation of your lease agreement, and you are all of a sudden on the ranch owner's private property that he's not leasing to you, and that's a lawsuit. And so being absolutely precise with these measurements is very important, okay? So surveyors do a lot for that, but mostly we use them for things like construction and if parcels of land need to be divvied up between different owners, things like that. So he was a surveyor in the 1700s. He didn't have that fancy tripod camera thing. He probably had a rope that he used to measure things with, but he also did a lot of walking. He did a lot of hiking. He did a lot of going out there. Someone said, hey, we're buying this 400-acre lot of land. Go measure it out for us so that we know exactly where it butts up against someone else's territory, someone else's property. He would walk it, right, and measure it and take notes and maybe leave little markers, right, little stone markers or little wooden markers, flags perhaps, okay? But as he did this all across England, he found a few cool things in the rocks. He noticed that he started seeing patterns. He would be in this part of England and he would see a rock that had certain fossils, and then he would be working years later in that part of England and see the same rock with the same fossils. Or maybe different rock with the same fossils. Or maybe the same rock with different fossils, but he started tying these things together. He started making these observations. And so because he had such wide access to England as part of his surveying job, he actually started keeping track of which rocks were there, which ones are exposed at the surface. And through William Smith, the first geologic map was made. This is a picture of it. These colors correspond to different types of rock that are exposed at the surface. Now, we use geologic maps now as an extension of what he started, not only to show the different types of rocks, but also their ages. We can color code a couple of different ways there. Okay. But yeah, fantastic invention, the geologic map. What a mind this guy had to collect all that data in his travels over decades and compile something like this. He also started to theorize about the principle of fossil succession. Do you remember what that is?
Fossils are the same age regardless of location.
Ooh, you're so close. It's not that they're the same age regardless of location. It's that if you have the same type of fossil present in multiple layers of rock, they are probably at the same time, regardless of the types of rock that they are. So that's probably where your mind was going, right? It's probably what you were thinking about. But basically, if I have fossil 1 in conglomeratic sandstone here, and then I go 100 miles away and I have fossil 1 in sandy limestone, I'm looking at two different environments, but the fact that they both contain fossil 1 means that they are at the same time. One was being deposited out here and one was being deposited out here. Now, while those different types of rock tell me about the different environment, for example, conglomeratic sandstone, probably a river delta. Sandy limestone, probably getting out into the deeper ocean from off the nearshore shelf. Okay. Both of those are having sediment deposited simultaneously. Both of those are having dead animals, that fossil 1, deposited in their sediments simultaneously. Okay, so I can make an environmental interpretation and be fairly certain that they are happening at the same time. Okay, so fossil succession not only includes that, but also if fossil 1 is present here and a slightly different version of it is present here and a slightly different version of it is present here, I'm seeing a distinct successive sequence of rocks. And I can chart that as my fossil changes through time. This is kind of an added element of the concept of fossil succession than you have learned in the past, because we can look at these fossils and chart which traits are changing as time goes on. Perhaps fossil 1 becomes fossil 1.1, and then 1.2. And then a slightly different change might make that fossil 1.21, right? If I don't know how many of you are following this. I'm kind of putting it in database management terms. Slightly different changes in the evolution of these organisms we can chart through the fossil record, helps us see the evolution of that organism through time. And then if fossil 1 disappears, fossil 2 picks it up, right? And we use that for the fossil succession. All right. Georges Cuvier. Can you guess what nationality he was?
French.
Yeah, he was French, right? Okay. Georges Cuvier, another naturalist, right? People kind of had different ideas for what fossils were, what they represented. Any of you ever heard any interesting theories about fossils? There are a bunch of wild ones that still float around today. Only last year, I had someone in my classroom who was thoroughly convinced, prior to taking my class, that fossils may have been from another planet. And when our planet was formed, a very strongly Christian person here, believing that the Earth was 6,000 years old, right? When the Earth was formed 6,000 years ago, the materials used to make this Earth came from other planets that contained the relics of dead things that used to live on that planet. It was a very interesting theory. I actually had a very fun conversation about it. Yeah.
It's not the most wild thing I've heard.
It's not the most wild one? Tell me.
One person, well, I think it was a teacher, he said fossils are fabricated by the government.
I've heard that one, that fossils are a scam. My friends, I have a confession to make. These are all styrofoam. I carved these from wood. I 3D printed all of them. Well, some of them, right? All of these, I invented all of them, right? Including the ones that I pulled from the ground myself. That's all a lie, right? So, very interesting theory. That holds up until you talk to someone like me. We can't all be government dupes or stooges. And with how often you hear me affectionately discuss our government and its decisions, I'm sure that you could definitely believe I'm a government agent. Yeah, that's a very interesting one. There is no shortage of government paranoiasts out there. To some extent, there are some things our government does that I absolutely am like, ooh, yeah, that's probably true, right? And there are other things that I'm like, it stretches the bounds of credulity, right? So that's one of them. He was a catastrophist. What is a catastrophist? We learned about this in 1403.
Theory that the Earth changes through massive cataclysms.
Yes. So catastrophism is a belief by those who do believe that the Earth is very young, okay, within the bounds of thousands of years. And this catastrophism is how they kind of explain the larger events or the larger changes that take place. Instead of the Grand Canyon forming over tens of millions of years, it formed from a giant flood, stuff like that. It happened very quickly, okay? So even though he was a catastrophist and he believed that these things happened extremely quickly to be within the bounds of creationism, he did lay some important groundwork for figuring out the history of fossils, for classifying them and the such. So instead of simply looking at a fossil and thinking, oh, that's that's from something that's dead now, but is probably alive somewhere else on the planet, right? This is just a dead one. He was the first person to actually start, or one of the first people to actually start theorizing, well, what if a catastrophe, like a giant catastrophe, completely destroyed a whole group of animals here? What if there was a giant cataclysm here, and everything around here died, and this a while ago, and now they're in the rock? He actually started asking those questions. He never quite left the bounds of catastrophism. He did all his studies within the sort of boundary he had made for himself, that shell of catastrophism. But he did start asking those important questions, which led later on to, after James Hutton, who we'll talk about here in a minute, who actually helped us start to understand exactly how old the Earth actually is, right? A combination of these ideas led to what we now understand of extinctions in the long past did wipe out massive populations that are preserved in the fossil record. Okay. So now let's talk about James Hutton. James Hutton from Scotland took decades and decades to make observations, and specifically observations about processes. This was his thing. He was all about the processes, how long these processes take, gathering that data. And what he found was it would be impossible for the processes that are happening now to make the Earth that we have today in the amount of time that everyone thought that the Earth had been around. You physically cannot make all of the things that we see today on Earth in 6,000 years. Not with what we see as natural processes around us, right? So what does that mean? What is the implication from this? The Earth must be older. And so his data, once he found it and he collected it, again, he spent decades collecting all this. He didn't even release this until late in his life, and his data wasn't actually, believed, widely held until he was dead. An unfortunate pattern with scientists. I believe it was somewhere in the neighborhood of about 200 million years is what he estimated the Earth to be in age. Now, you start telling people, a whole population of people who have this strongly held Christian belief that the Earth is 6,000 years old, and you tell them the Earth is actually 200 million years old, you'd be like, put this guy in a straitjacket and lock him up in a padded room, right? And being treated like that was often a situation for people who believed these theories, right? But eventually, his data could not be denied. As more and more time goes by, and there aren't these giant cataclysms, these giant catastrophes to justify a catastrophism, fewer and fewer people could believe in it. And instead, they would turn to the actual, reasonable, logical conclusions drawn by this person who spent decades collecting all of this data. It lays some important groundwork for what we call the scientific method today, which is largely data collection and analysis driven, right? Instead of simply drawing a conclusion, making observation, drawing conclusion, that's not science. What is that? Huh? Guessing can be, but there's an overall word for this. When you make an observation, when I see something and I make an observation about it without trying to justify it whatsoever, no, it's an opinion. Yes. This is the difference between science and an opinion, right? An opinion is something that you make based on internally held beliefs, and that's it, right? My opinions have changed a lot between when I was a teenager and where I am now, okay? Some of them I still have pretty deeply held. Some of them have only gotten stronger. I'd say somewhere about 70% of the opinions I've had have changed over the last 15 years, okay? But there's a difference between that and science. In science, using the scientific method, we make that observation, yes, but then what do we do with it? We make a hypothesis, a possible explanation, and then we seek to figure out if it is true. We do the work. If we fail to disprove it, it has become a theory. Still not guaranteed. Simply failed to be proven wrong. Right? Ringing a bell? Making sense? Remember this? Did I do the golf ball exercise with y'all? No? You think we did? I think I did it with your class when you took 1403. You don't remember it? All right, I've got a case of golf balls over there. What time is it? 10:16? We probably don't have time. But in this exercise, what I would normally do is I would hand a golf ball to each one of you and then just ask you to give me data points, right? Make observations. So some of you would say it's got dimples. Some of you would say it is white. Some of you would say it feels lighter than it should be. Some of you would say it bounces. Some of you would say it's got characters written on it. Some of you would say it's made of plastic, right? Things like that. And we collect all this data about this object that we do not know what it is, by the way. We're going to draw a conclusion after we have applied the scientific method. So with all of this data, now we make a hypothesis. With all that information, some of you would say it's meant for a sport of some kind. Some of you would say it's intended to be a weapon. Some of you would say it's a child's toy, right? You would make all of these different hypotheses. Well, then what's the next step? Testing it. How would we test it? Well, to figure out if it's a child's toy, maybe we give it to a child and see what they can do with it. There's only so many things that a child can do with this. But it may still be true because the child plays with it. All right, well, that's a possible hypothesis. Cha-ching. Now let's test it and see if it's a weapon. Well, when you propel it high enough, it goes pretty fast, but it breaks apart pretty easily when it hits something harder than itself. Not a great weapon, okay? It's actually fairly soft compared to a bunch of other materials. Could be used as a weapon, but not ideal. Maybe not that, but possible. Then we see if it's meant for a sport. Well, we see when we start hitting it with stuff, maybe like with a baseball or some other propellant, we launch it from something, it flies pretty fast through the air. Oh, and it also bounces pretty well. Those dimples, they actually increase its velocity in the air. They make it more aerodynamic. It's made out of materials that will flex upon impact and bounce off of that, preserving a lot of its momentum. At the end of this exercise, we would find that there are more data points, more positive, possibly true data points, pointing towards the fact that it is meant to be used as some sports object more than a weapon, right? And so we would have to draw the conclusion that based off of the data we have and the testing we were able to do, the most likely hypothesis is that it is in fact meant for a sport of some kind. Although what the sport is, we don't know, right? That would require more testing. This is how you apply the scientific method, okay? This exercise usually takes 20 minutes or so, and we don't really have that kind of time. Okay, so now we are going to do a different exercise, though. Go ahead and pull out a piece of paper. How many of you have pieces of paper? No one? If you got paper, pull it out. If you don't, share. Ask someone else for a piece of paper. Do I have paper in here? I have some. Does anyone need a pen? I've got pens. Pen? 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 Yeah? Yep, pen? Pen? Alrighty. I may have done this with y'all in 1403, but we're going to do it again.
Do we need a pen or is simple?
Pencil's good. Any kind of writing instrument.
Oh, I know.
You know what we're doing? We're discussing geologic time and the ways we break it up. So you're going to make something like this, okay? With the box. Do you remember this? Some of you, it's been a while since some of you took my class, so we're going to do it again. So make a long box and then split it into 3 separate boxes. All right. Now in this leftmost box, which is labeled time interval, starting from the bottom, you're going to write these words. When you were born, when you learned to walk, when you rode your first bike, when you started 3rd grade, when you started 4th grade, and when you learned to drive. Just those words, no dates or anything, just the words. And you can shorthand it, right? Born, walk, bike, 3rd grade, 4th grade, drive, right? You don't have to do this exactly, just the words. Now, in this numerical time column, that's where you put the dates associated with those events. Like so. Of course, obviously yours, not mine, right? Don't copy my dates. That's identity theft. Although it would be weird if you had the exact dates as me. I don't think that's ever happened. Been teaching this class for 5 years. I don't think anyone's been exactly my age to have the exact same dates that I did. Some of us have to do a little more math than others.
You're asking me to go way back. Use all my fingers and toes.
Right? And it's very possible some of you may not even know how to drive yet. It's possible some of you may not know how to ride a bike. That's happened before, for sure. That only adds to the depth. That adds to the plot a little bit. Okay? Now draw a horizontal line between the bike and 3rd grade. And in that last column, sequential time. Above that line, you're going to call that stage of your life the Schoolean, and beneath it, the pre-Schoolean. So what have we done here? We have taken events from your life and divided your life into 2 different time periods based upon your life events. From 3rd grade up, you were in school. You started school, right? And so that period of your life we call the Schoolean. Everything before then is the pre-Schoolean. Now, notice that we start 3rd grade here. I don't have 2nd grade or 1st grade or kindergarten, right? This is the only data point that I asked for. The fossil record is not complete, my friends. It's very possible that there may not be any pictures of your 1st or 2nd or kindergarten grade experience, right? I don't know it exists unless there's evidence of it. Maybe you went straight into 3rd grade because that's the only picture you got in your photo album, right? Just like that, the fossil record is incomplete. Whatever led to point C must have been A and B, but I don't have fossils of it. I can only assume it existed, right? So I have to work with the data I've got. So even though there were time periods before 3rd grade here that you were in school, I don't have data for it. And so between this data point and that data point, when you were in school, happened somewhere in there, so I draw that line between them. This is how the geologic time scale works too. First reptiles, bing, draw a line. First amphibians, before that, bing, draw a line. First bacteria, way before that, bing, draw a line. First mammals, way above that, bing, draw a line. And these lines are ever so slightly moving all the time as we find more fossils to adjust those times. Okay? So even though we'll say the Triassic started 270 million years ago, it's very possible that tomorrow someone could publish a story saying, hey, we actually found evidence that the first dinosaur was a little bit before that. And so it could shift down a million years. Right? That sort of thing happens. We're filling in the fossil record more and more as time goes on, making these dates a little bit more accurate. So we get something that looks like this, okay? Where we have eons, eras, periods, and epochs, okay? Epochs, epochs, whatever you want to call those, okay? That are the sequential time. The biological events are your time intervals that we just did, and the years are the numerical time. So here's our geologic time scale. Just like with your driving and your bike in your 3rd grade, and you're going to sneeze. I did it! Has anyone ever done that to you where you're about to sneeze and they yell, pineapple, and then it's just gone?
Yes.
Pineapple, for some reason, it takes that sneeze right away. No? Next time she's going to sneeze, yell pineapple in her face. Watch what happens. All right. Was he going to sneeze? You just did it for fun. Okay. She's going to come for you. All right, so these are your biological events like the bike and the 3rd grade and driving and all of that, okay? Look, origin of mammals right there. Dinosaurs and true flies, right? Things like that. First amphibians right here. First spiders, scorpions, things like that, okay? So we draw those lines there, and that's where all of these time distinctions come from. Now the eons, those are the largest time interval. We've got a series of eons, the Hadean, the Archean, and the Proterozoic, that collectively we refer to as the Precambrian. Okay? These are each their own eon, taking up most of geologic time. This small little section, these 3 eons right here, go from 4.54 billion years to 541 million years. That's 4 billion years of history that we just kind of lump right here. Why is so much more of the geologic timescale dedicated to what comes after in the last 500 million years than the first 4 billion? What do you think?
More evidence.
More evidence of what?
What happened?
Through what?
Those are too deep that we can't make.
Well, sure, there's less of that exposed at the surface, sure, but that's not the main reason. There's enough of it exposed that we could talk about it more, except for what? And I really want to dig into what you're thinking here. You say there's more evidence. More evidence of what? Life! Bingo! Okay? Sorry if that was too exuberant, right? Wake up, right? Okay, so yes, in the last 541 million years, life has really skyrocketed. Diversification of life has just logarithmic, exponential in the last 541 million years. There was some before, starting in the Archean, none in the Hadean, starting in the Archean, and then definitely more in the Proterozoic, but it was bacteria. There wasn't a whole lot, right? Just tiny little organisms. We've got some of that. Can't read much into it. But starting here, 541 million years ago, boom, way more. And so, yeah, we do have the first 4 billion years of Earth history lumped into these little sections here, and the rest is given all that on geologic timescales. It's obviously not proportional, right? If it were, then we would have this be spread all the way up here, and the last 500 million years would basically just be from here on up, right there, okay? But we're not doing that. Okay, so eons. Okay, so the Hadean, the Archean, and the Proterozoic. And then the Phanerozoic eon is the one that we are in, the one that began here at the Cambrian, where life really began taking off, like I said earlier, started there, still going on today, Phanerozoic eon. And then there are eras. Each eon is broken up into eras. These ones also have eras, but because there wasn't too much life, we don't really talk that much about it, at least not within the bounds of this class. If you were to take a more in-depth geologic time class, say at a university for a master's program, you would probably go into those, right? But the eras that we are most interested in, the Paleozoic era, think of this as your pre-dinosaur life era. And then once dinosaurs show up, we've got the Mesozoic era. That's kind of the age of dinosaurs. This includes the Triassic, Jurassic, and Cretaceous that everyone knows so well. And we live in the Cenozoic era. Think of that as the post-dinosaur era, or the age of mammals, okay? So pre-dinosaurs, age of dinosaurs, age of mammals. Think of it like that. Paleozoic, Mesozoic, Cenozoic. Then we've got periods. Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian, Permian, Triassic, Jurassic, Cretaceous, Paleogene, Neogene. In the United States, we break the Carboniferous up into the Pennsylvanian and the Mississippian. We have a lot of rock here that we can easily distinguish between those. In the UK and Europe and over there, they don't really do that. They just kind of collectively refer to it as the Carboniferous most of the time. It's kind of an American thing more than anything, but they'll know what we're talking about. Like if I was to talk to an English geologist and talk about the Pennsylvanian, they would know what I was talking about. It's just, in their textbooks and in their lectures, they don't typically distinguish between the two. They might more now, but they didn't not that long ago. Okay. And then there is the epochs, okay? I usually pronounce it epochs because if I say epic, people think I mean E-P-I-C. So I try and distinguish that, right? Epoch. Okay, so there are epochs all throughout all these periods. Just like every eon is separated into eras and every era is separated into periods, there are lots of epochs in these periods as well. The only ones we're going to worry about in this class are the ones that have occurred the most recently. Okay, so here in the Cenozoic. So the epochs we're going to be talking about are the Paleocene, Eocene, and the Oligocene. Those were in the Paleogene period. And then there is the Miocene and Pliocene. Those were in the Neogene period. And now we are in the Holocene. Okay, the Pleistocene ended with the Ice Age at the last glacial maximum, 11,700 years ago. We are now in the Holocene. There is a fairly large movement, which is gaining a lot of traction in the scientific community, to rename the Holocene to the Anthropocene. Do you know what that means? What is anthropology? What is that word? Yes, humans. It has to do with the study of humans. If we give all of these times, all these different divisions of time, a name and a separation from each other based upon biological events that are the most significant, then for the last 12,000 years, since the end of the last glacial maximum, what's been the most significant biological event, do you think, to happen on our planet? Yeah, the development of human civilization. To the point where we are actually contributing to an entire climate shift. I say contributing to because remember, we didn't start it. We've only added to it. Okay? But that's some pretty incredible power we've got over our ecosystem, which, yes, means that we are probably the most influential biological organisms on our planet in the last 12,000 years. So there's a large group of scientists and environmentalists who kind of want to do it to cast blame and aspersion, but whatever, who believe that we should be calling this time, this epoch, the Anthropocene. So it's very possible that they may actually change that here pretty soon. Huh? You concur? And it's a fair argument. We are the most, influential on this time period. I personally think it's a little hubristic to name an entire epoch after ourselves. But if we're the ones naming it and we stick to the same, I can see the reasoning behind it, right? If we're sticking to the same naming criteria, Yes, sure, we are the most influential, but it also feels a little weird to name it after ourselves, by ourselves. But I guess we make the rules anyway, don't we? Okay. So we differentiate these time divisions based upon events that occur. So there are fossil occurrences, right? We would not know when the first reptiles were unless the first reptile bones show up in the fossil record, right? So those fossil occurrences are a major way that we do these distinctions. But what if there are no fossils? Then we have lithological differences, okay? So lithological continuity, right? That means that you have the same sequence that keeps going through smoothly, transitioning from one sequence to another. Now there are some that break partway through. There's missing time. I'll talk about those here in a minute. Those are called unconformities. I'll get to that in a bit. But let's talk about fossils a little bit. We use fossils to separate time from each other, but there are some criteria that those fossils have to follow, okay, have to hold to for us to be able to use them consistently as these division markers, okay? And it has a lot to do with being an index fossil. You remember we talked a little bit about being an index fossil and what is required for that? Abundance. You need to have a lot of you. If you have a species and there's only ever a couple thousand members of that species, it'll die and go and probably won't leave anything in the fossil record. But if there are billions of you, you're going to be in the fossil record. Humans are going to be in the fossil record. There's been enough of us for long enough that we will be in the fossil record. Absolutely. Right? Same reason why there are crabs in the fossil record, and trees, and dinosaurs, because there was enough of them spread out that they were in the fossil record for sure. So, between the Precambrian and the Cambrian, from all the way from here to here, almost nothing of note. Not much diversity, just stromatolites. And then all of a sudden, shabam. Life everywhere. Complex. Hugely diverse life everywhere. So different from what we had before. So this change in abundance meant that there's a lot more fossils to be found, hence why we can get more detailed with our distinctions of geologic time past that point. This is also true for changes in diversity, which we see there. Abundance and diversity both picked up at that point in time. We already talked about William Smith and how he gave the idea of that fossils don't just occur randomly. They were alive during certain time periods and can be found in certain layers of rock that represent ecosystems. Okay? Non-random distribution, in other words. I have these trilobites here so that you can kind of see some changes that happen over time. All of these are trilobites, but they are all different from each other, which is why trilobites work really well as index fossils, because of the incredible amount of diversity present here. Okay? So this and this and this and this and this and this, you can tell that they are all part of the same animal group, right? Pretty easy to see. But this one's a bit broader. This one's a bit narrower and has longer cephalon horns here, okay? This one has a fatter pygidium, okay? This one's got a narrower, longer pygidium and longer cephalon horns, okay? This one's got rounded kind of eye bulbs on its cephalon. This one has really crazy long Fu Manchu looking, cephalon horns. And it's got spikes coming off the back and it's a much narrower body profile, but they're all clearly trilobites. This kind of diversity is what we use to classify index fossils. Yeah, so roaches are insects. Insects are arthropods, and these were some of the earliest arthropods. So even though trilobites went extinct, roaches and other insects have common ancestry with them. Yeah. Okay, stratigraphy. There are different kinds of stratigraphy. Okay, so the one that I did this lab with you on is lithostratigraphy, with a little bit of, there wasn't really any biostratigraphy. Lithostratigraphy is what we were looking at here. Lithostratigraphy is using rocks and changes in rocks to classify time in the sequence. Okay, but we use something called correlation here. I've already kind of explain what correlation is. Using this data to draw conclusions about a more general area, okay? If I get a core sample here and here and here and here, and this table represents a 1,000-mile cross-section, and I'm getting cores all along this, I can only get 5, but I can make interpretations about that entire 1,000-mile cross-section by drawing correlations between all 5 core samples. This is common in the oil field. I've done this in the oil field. I've done it in the mining industry. Okay, it's a common practice among pretty much anywhere that is interested in understanding what's going on underground. So the different types of stratigraphy. Chronostratigraphy. You use chronostratigraphy if you want to partition these layers by their time, not by their rock type, not by their fossils, clearly just simply by the times they were around. That is a chronostratigraphic method. Okay? Biostratigraphy is interested only in the things that were alive during this sequence of time. So for example, here we have 2 different time periods, okay? 2 different epochs, represented by these 2 differently colored lines here. I have several different types of organisms, just a couple of which you can see what their different fossils look like, okay? All within the same general species, or not species, but genus, okay? But each one of these different lines represents a different species. Where the arrows are pointing down, that means that that species came from down there, okay? So it's been coming from down here and it goes up here. Where you see the species pointing up, that means that it continued past that point in time, okay? How many more species do you see that came in from this time period versus how many left? The ones that were alive during this bottom time period, let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. 28 that were alive during this bottom time period.
26 made it.
Yeah. Only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 species made it past this second one. What happened? What happened? What'd the dog do? What happened? Yeah, there was some kind of extinction event. We went from 28 species that were alive down here to only 10 that made it past here. Something happened. Something probably intense ecologically happened to cause this. And by the way, look at all of the different species that died off right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 of those 28 died. Boom, right there. A few more began and then died off because they just couldn't cut it. A few began and kept on surviving. They were able to adapt to whatever the ecological difference was. Okay, this is biostratigraphy. Drawing conclusions of this stratigraphic column, not by studying the rocks, but the behavior and patterns in the fossils present. These are those characteristics for an index fossil that I mentioned earlier. Short duration, abundant population, widespread habitat, unique physiology. Like those trilobites, we could tell them easily from each other, but also see that they were in the same group. That's a unique physiology. Move on. Okay. Magnetostratigraphy. This is when we look at the magnetic particles in your layers of rock and even in your fossils to figure out what Earth's magnetic field was doing at that point in time. You remember how it can fluctuate back and forth. It goes through polar reversals every now and then. We can track through a stratigraphic study. Okay? This is magnetostratigraphy. Each one of these black and white bars that you see here represents a different chron. So a sequence of crons is given a designation. This is chron C5, C5a, C5b, C5c, C5d, right? So on and so forth. You can see our geologic timescale here. So here's the Quaternary, here's the Miocene, the Oligocene, going all the way here. Here's the Pliocene, or the Paleocene. Here's the Cretaceous right here. So past this point and all the way through there, that's all mammal time, right? This is dinosaurs. You can see right here, there was a transition right there at the end of the Cretaceous, probably correlating with whatever the catastrophic event was that killed the dinosaurs, right? Some sort of chron shift happened then. But you can see where the black is and where the white is, those are polar reversals. So during this black time period, right, magnetic north is north. During the white one, magnetic north is now in the South Pole. And then it goes back and forth for different lengths of time. You can see up here, we are in this sequence. Magnetic north is in the north. And it's been there for a nice long time. We are seeing that shift, though. It's wandering further south, and we've been in this for a nice long period, which is why we're thinking we're probably getting set for another reversal here pretty soon. Okay, so that's magnetostratigraphy. And then lithostratigraphy, we already talked about. That's where you separate the layers of rock by the rock type. Okay. So these are a couple different examples. These are not the only ones. Just a couple of the more common examples of stratigraphic correlation. Any questions about this? Okay. So let's talk about the history of how we figured out how old the Earth is. Okay. There have been a few attempts to figure out the age of the Earth throughout science. And here are a couple of the high marks. Okay. How long did it take for the oceans to get salty? Right? So the problem with that is if you assume that the oceans got salty over time, you're assuming that they started off fresh, and you're assuming that the Earth was started, that the oceans were there when the Earth was formed. Okay, so there's a couple of assumptions here. This is incorrect. The oceans did not start fresh. If anything, they started nasty. Okay, they were probably filled with ammonia and methane and all sorts of other things as they eventually got deeper, and as the atmosphere stabilized, and as more oxygen was put into the atmosphere, allowing for oxidization of some of the compounds in the ocean. Okay, a lot of that nasty stuff left. Salt is one of the most common covalent bonds on our planet, right? It happens very easily. It can happen very easily. And so salt often makes its way out in a dissolved state to the ocean. And so our oceans did get saltier, but they did not start fresh, if that makes sense. And they have been more and less salty as time goes on. There's a fluctuation. It's not like there's been a steady increase in salt as time goes on. Okay? Huh?
It's disproven?
Yeah, it's disproven. You can't use that to determine how old the Earth is. What about how long it took for the Earth to cool? Now this one is a little more interesting, because we do know that the Earth is in a state of cooling. It has been cooling. However, there are some other assumptions in there as well, namely that the Earth cools at the same rate on the outside as it does on the inside. And so by observing what we can here at the surface, we're essentially assuming that the same is going to happen on the inside at the core. That's not true. We've done enough lab experience to know that pressure will affect that, okay? As well as the presence of radioactive elements at the center. Okay, so it's going to keep things a little bit hotter for longer. So we can't accurately measure the age of the Earth simply based off of its cooling rate. But also, the fact that the Earth's cooling has been kind of reset at different points in time. We got hit by another planet, right? Making our moon. Earth's cooling would have completely restarted by then, right? But then there's radioactive decay. Now we're talking. Radioactive decay is a much more reliable method for determining the age of a thing, because radioactive decay is consistent. No matter where you are in the universe, radioactive isotopes will decay at the same rate. It's a constant. A uranium-235 element here is the exact same as a uranium-235 element on Tau Ceti beta. Okay? 10 light years away. 12 light years away. I think it's 12. They're decaying at the same rate. Okay? So this is much more consistent of a dating method. So we can measure alpha, beta, delta, all these different radiation types that are coming off of these radioactive elements. And this is where we get things like radioactive clocks, radiometric clocks. Okay? There's a thing called universal time. You ever heard of that? Universal time. You know how there are different time zones around the planet? So like right now, it's the middle of the night tomorrow in Australia, right? They're already in Tuesday. Let's see, what time is it? It's almost noon. They're almost into Tuesday. Okay? It'll be Tuesday here for them in a little bit, I believe. Okay? So they're not ahead of us, literally. They're not time traveling ahead of us. It's just that right now for them is at a different point in time because they're on the other side of the planet and the sun is on our side. Okay? The exact same moment in time is happening for both of us, but we have different perspectives on it because of our position on the planet. So people were like, okay, well, let's just make a universal time. So there is something called universal time, which is based off of an isotope clock, a radioactive isotope clock. I believe it's held in Greenwich, England. Okay? This radioactive clock you can look at and coordinate all time based off of that. Whenever I have a phone conference with people in Australia, which happens more often than you might think, we usually go off of Greenwich time because it's just a much easier thing to schedule, right? If I say 2 p.m. CST, to us that's 2 o'clock our time. But the poor Australian on the other side might lose track of when exactly that is. But if we're both using the exact same time based on this radioactive clock, then we'll both be on the same page, so to speak. Okay? All right, so we use radioactive isotopes that decay at the same rate to figure out how old things are. This has to do with half-lives, right? A half-life is a half-life is a half-life. Continues at the same rate. After a certain number of half-lives, I will only have a certain amount of my original material left. In the case of uranium-235, that's 704 million years. After 704 million years, half of my uranium will be lead-207, right? For uranium-238, it's 4.6 billion years. Oh, but it might be more than that. It might be a little bit more than that. We only think it's 4.6 because that's our oldest frame of reference for uranium, right, is here on our planet. So it might actually be different than that. That's just what we're going off of. Okay, potassium-40, 1.3 billion. Oh, rubidium-87, 48.8 billion. It has a half-life of 48.8 billion years. How do we know that? We can see it out there, shining at us. Okay, so, and we have a little bit of it. And we can determine, okay, only so much of that half-life has passed. Okay, only so much of this has turned into its stable daughter, strontium-87. Okay, and then of course there are fossils, but fossils are good relative to each other, not necessarily versus or relative to the entire date of the Earth. That's why radioactive elements tend to be a little bit better for a holistic view of how old a thing is, independent of reference to another fossil. But fossils are great when you have that point of reference. Okay. Event stratigraphy. This is where we use things that happen in the fossil record or in the lithological record to make reference points or reference layers. Okay. So I told you earlier about certain events that can happen. Things like volcanic eruptions. Guess what? That leaves ash, right? In this picture right here, you've got the Long Valley volcano, which erupted right here on the border of Nevada and California, and deposited ash all across these states. So if I were to go out there, and if I were to dig a hole in Kansas, I would find a thin layer of that ash in the soil under a certain depth. And I could correlate that same marker bed of ash to Nevada, right? To New Mexico, to Southern California. It doesn't show it on the map, but into Mexico as well. It did go into Mexico for a while, okay? I can correlate that same layer of ash across any of this place where the ash went. That's a marker bed, okay? Same thing with glacial deposits. Asteroid impacts. When an asteroid hits, it's instantly, well, mostly vaporized, okay? A bunch of that asteroid is vaporized. A bunch of the material on the Earth's surface is vaporized and gets blasted into the high atmosphere, and then it gets kind of sifted over the course of the planet, over the atmosphere, and is filtered down. So the asteroid that killed the dinosaurs hit off the Gulf of the Yucatan Peninsula, what is now the Yucatan Peninsula, right? But we find layers of ash from that impact in the Arctic and in the Antarctic. Yeah. It put ash all over the entire planet. And that marker bed, we can correlate anywhere as being, boom, that's the end of the Cretaceous. Okay? Unconformities. I'm going to go back here to this picture. An unconformity I talked about before is where we have missing time in the rock record. Why would we have missing rock? What could happen that could lead to having missing rock in a stratigraphic column?
Maybe water washing away or something?
Oh, there it is, right off the bat. Weathering and erosion. That's what does it. Right? There's no naughty rock gnome that goes and steals the layers of rocks. It's going to be weathering and erosion. That's where we get this missing time. And there are a couple of ways this can happen. You can have a disconformity, where we have layers of sedimentary rock, and then there's a weathering erosive event, and then sometime later, more layers of sedimentary rock. So this could be 2 billion years old, and that could be 40 million years old. We've got that much missing time. That's a disconformity. A nonconformity is when you have igneous or metamorphic rock, say like a magma chamber, that has a weathering surface on it, and then sedimentary rock is deposited on top of that. Okay, so that's a nonconformity. An angular unconformity is when you have layers of sedimentary rock that have been tilted at an angle, and then horizontal layers of sedimentary rock deposited on top of that. There's one of these in Scotland called Siccar Point, S-I-C-C-A-R, Siccar Point. If you're ever in Scotland, pay to visit. It's really cool. It's one of the geologic features that made James Hutton think, I don't think things are happening the way that we think they're happening, and why he started collecting that data. It was one of the things that inspired him. Okay? Very cool. Angular unconformity there. And then the last one is the hardest one to interpret. It's a paraconformity. We have layers of sedimentary rock, and then an erosive event that left a flat surface. This probably is actually just no deposition. A period of no deposition. This might be thousands of years or millions of years. There's just nothing being deposited there. And then more deposition on top of it. So we go flat layer, flat layer, flat layer, flat layer, flat layer, and you might not even know there's a paraconformity there until you did an age check. And then if you did a radioactive check, you might realize that is 75 million year old rock, and that is 40 million year old rock. There's 35 million years of time missing there. Paraconformity. Okay? So those are marker beds. So we use correlation for, I already explained a little bit about cross correlation here. This is just a visual example of this. We can use seismic data to gather information about what goes on underground. Okay? I already explained seismic data to you. We collect it by blasting sound waves underground. Do you remember this from 1403? Sonar. Sonar is that bing that ships and submarines put out so that the sound waves can bounce back to them and they can collect data about how close things are. Well, you can do that with geology as well. Okay? So we send the bing, the sound wave down underground, and it'll bounce off of different layers of rock at different speeds and come back at different frequencies. So we collect all that data, throw it into a machine, and it spits out something like this, which looks like a bunch of static noise until you learn how to read it. Okay? And then you can start saying, okay, well, look, there's a layer here, there's a layer here, there's a layer right there. And then you can draw some interpretations. You can make something that looks like that. Okay? You can color code it to represent different layers of rock. And if you're looking for, say, oil, then you'll collect that seismic data, make those interpretations, and then with just that data, you can go to your oil executive and you can say, hey, based on what we're looking at here, we believe there may be oil at this high point in this formation. Because look, if we're following this formation right here, okay, you see that darker line? That may be an oil-bearing formation, okay? So here's a high point. Oil may be collecting up there. Look, there's a high point here. Oil may be collecting in that. So let's drill a couple of exploratory wells and figure it out. So the company says, sure, you have $10 million to explore this location. Go for it. So you say, okay, let's drill a well right here. We'll get a core sample. Let's drill a hole right here. We'll get a core sample. So now all of a sudden, not only do I have seismic data here, I've got 2 core samples that I can correlate as well. So I can use those core samples to not only prove my interpretation of this, but to fill in some of the gaps, right? So if I think I've got oil here, I'm going to drill all the way to there, and I'm going to drill all the way to here, and I can actually chart where these layers meet up and interpret what's going on there. I can say this layer of sandstone is that layer. I can say this layer of sandstone is that layer. So on and so forth. You can follow the trends here to match them up with each other. This is cross-correlation. Questions about correlation or about marker beds or anything like that? No? Okay. Earth's temperature changes quite often. It's changing today. It's changing right now. It will change more in 100 years. It will change a lot more in 1,000 years. And it'll change probably a heck of a lot more in 40,000 years. Okay? We might be in the middle of another ice age in 20 to 30,000 years. Who really knows? Right? But it changes all the time. And a lot of its change is based upon Milankovitch cycles, which we've already discussed. Right? The precession, obliquity, and eccentricity of Earth's orbit around the sun. Where our eccentricity is how elliptical our orbit is. We go from a near spherical orbit to sorry, you don't like that noise, huh? To an elliptical orbit on about a 100,000 year cycle. Okay? So Earth is doing this around the sun. Okay? Then you've got the obliquity. The obliquity is that axial tilt, which you can see right here. Why do we not build our globes to do this? Does that annoy anyone? It's a little annoying, isn't it? It's okay to say it's annoying. Why do we build them on this tilt? Well, because Earth is on a 23.5 degree tilt versus our axis around, or the plane of our ecliptic around the sun. Okay, 23.5 degree tilt, which is why the equator does that weird thing. Okay, so we always have this relative to the sun as we are at the 23.5 degrees. Okay, so that's our obliquity. Now, our obliquity actually fluctuates back and forth, like this. Okay? So this is happening while this is happening while this is happening. So our planet is always doing this through space. I hope you don't get dizzy by just staring at that, right? Imagining how we're spinning through space at 200,000 miles an hour right now. Okay? So because of these different movements of our planet through space, different parts of the Earth are exposed to the sun and absorbing radiation at different rates, at different distances, depending on where we are in our elliptical orbit or spherical or circular orbit. Okay? So the further we are, the less energy we're absorbing. The further we are, while the most ocean is pointed at the, or Antarctica or Arctic is pointed at the star, at our star, we absorb even less, and that's when we enter into a cooling cycle. And then when we're closer and more landmass is pointed, we enter into a warming cycle. So these can affect that. Okay? So by figuring out what temperature and environmental changes happen through the fossil record, we can determine what sort of cycles Milankovitch cycles, or excuse me, what sort of history Milankovitch cycles have had on Earth in the past. And then you can get things like glacial effects, those global warming effects, all of that. All of those evidences are also preserved in the fossil record. Then we get transgression and regression sequences. Transgression is when the shoreline moves inland because the sea levels are rising. Regression is when the coastline moves oceanward because sea levels are falling. So if I see a sequence of shale sandstone, I can usually look at those as transgressive, regressive sequences, right? So if I'm going from deep water sediment and then up the stratigraphic column, younger in time as I go up, right, to nearshore sediments, I'm looking at a regressive sequence. And the opposite is also true. So here we have lagoon, barrier island, and then deeper water, okay? So you can see that my lagoon deposits, as time goes on, are going on top of my barrier island. My barrier island deposits are going on top of my deeper ocean sediments. This means a regression to me. Near shore on top of deep shore, or deep ocean, means regressive. The opposite is true, right? If I get barrier island on top of lagoon on top of beach, I'm going deeper over shallower, transgression. And then I can see them zigzag back and forth, showing me transgressive, regressive through time. Here's an example of that, okay? This is what the sediment looks like under Paris, France. We've got a bunch of Cretaceous chalk, and then an unconformity. And then we have nearshore, or nearshore. And then this is land, okay? This is terrestrial, okay? So we have beach, land, beach, land, beach, land, beach, 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 right? And then up until all of this, there was a lot of ocean on top of Paris, where Paris is now, for a long time. All this marine sediment, the sandstone and shales and all that. And then a massive regression, and now Paris is on land. This is partly due to the fact that Africa is running into Eurasia, uplifting a whole bunch of Eurasia as it goes. Okay, a whole bunch of Europe. But you can see where it went back and forth, right? Transgression, regression, transgression, regression, transgression, regression, big transgression, regression, a huge transgression, major regression, where we are now.
How does, like, Venice, Italy work with that? Like, what is it sitting on?
Venice isn't sitting on much. It's sitting on, if I remember correctly, I think Venice might be an island that's connected to Italy. Either that, or it's just a very low-lying, swampy section of Italy that is being reclaimed by the ocean. I don't remember exactly what the geology of Venice is, only that it is being submerged.
Back into...
Yeah, it's being flooded back into the ocean. A lot of the buildings in Venice actually are built on top of older buildings that are underwater. Yeah.
Another city I heard, I was thinking is Mexico City. I heard.
Mexico City was built on a lake. Yeah. Mexico City is, I forget what the original, I believe it was a Mayan city that was out there. And they built Mexico City around that ancient Mayan city, but that Mayan city was built on a lake that ended up drying out.
I thought it was built on the ruins of the Aztec city that was...
It might be Aztecs I'm thinking about, not Mayans. Again, not an archaeologist, right? Yeah. There's a whole bunch. Yeah, it is, because it's built on a bunch of sediment, essentially, it does have problems with buildings sinking into the soil. There's a whole bunch of buildings, like there's a city under the city of Mexico City. I'd love to go and explore it sometime. Who knows what's down there, though? It's probably where a whole bunch of certain organizations hang out. Yeah. Okay. Any other questions? Comments? Songs? Dances, maybe.
Songs?
Yeah, songs, dances, jokes, anything? No? All right. Well, I'm going to introduce you to Lab 3. All right, everyone, this is Lab 3. Real nice guy. Likes long walks on the beach. Okay, so we are discussing invertebrate fossils. Labs 3 and 4 are going to be largely, there's going to be a few questions, but then and a few like matrices that you put X's on to fill in the blank sort of thing. But then most of these are going to be kind of easy, just compare picture identification exercises, which I do have some hard copies for in that box over there. I can take them out if you want, but you can easily do this just using the Excel spreadsheet. Okay, so the Excel spreadsheet and this PowerPoint is going to be important. So there's a few things that we've already discussed here. Invertebrates are this section of our phylogenetic tree. Okay, so just a few things about the organisms you're going to be looking at. Brachiopods and bivalves look very similar to each other. They both have the two shell joined by hinge design. Okay, the difference is in their symmetry. Brachiopods have a symmetry that is left to right. So you can see here, if I were to slice this brachiopod down the middle, looking at it from the front, the left half and the right half would be the same. Same from the top down and bottom down view. Left and right are the same. Left and right are the same. Okay, so they have that left to right symmetry. Whereas with a bivalve, I have to slice it down the side. And the top and the bottom will be symmetrical. So here I'm looking at this from the side view. And I can slice it left to right. Those are symmetrical. I can't do that from the top down or the bottom up view because they will not be symmetrical. Only from the side are bivalves symmetrical. Okay, like an oyster, where the two halves of the oyster match perfectly, but when you look at them from the top or the bottom, they've got that curved shape. Right? Think about a banana. The curved shape of a banana. I can slice it down the middle in cross section and get generally equal halves. Or I can slice it down lengthwise. If I'm looking at it, like if I have my banana right here and I slice it like that, they'll be equal. But I can't slice it, if I have my banana curved like this, I can't slice it like that and get the same size. Right? They're the same shape, right? They won't mirror each other. Okay? So left to right, and then top to bottom, or side to side, I should say. Okay, top to bottom when you're slicing it from the side. Okay, so there's your bivalve. That's brachiopod. Now notice that I've got the dates for these things: 500 million years ago to now, 541 million years ago to now. Right? Those are going to be important for your lab exercises. Nautiloids and ammonoids are also difficult to tell apart from each other. Here's an ammonoid. Here's a nautiloid. Just by looking at them, can you tell me the difference? Hardly. Put this in front of the camera. Ammonoid, nautiloid. Hard to tell the difference unless you know what you're looking for. So let me tell you what you're looking for. Okay? Ammonoids will commonly have a little bit more complex suture patterns. Sutures are those lines that you see between the chambers in this shell. These are sutures right here. Each one of these chambers either holds the animal, the cephalopod, kind of think of the squid, that lived in the first few chambers, and then the rest of them in this coil were used to hold gases for buoyancy. Okay? So these sutures between these chambers in a nautilus, a nautiloid, are going to be nice and uniform and smooth, not really complicated. Whereas with many ammonoids, they undulate, and some of them get pretty complicated. There are some with suture patterns so complex that they're dendritic. They look like tree branches. They're doing all sorts of crazy squiggles. Very fascinating reason why. Nautiloids actually came first, right? Ammonoids 419, nautiloids 475. These came first. These came later, and part of their big evolutionary difference from nautiloids was the fact that they developed these more complex suture patterns. Why would they do that? Well, when you have a shell that's broken up into these sections, or that's separated into these sections, Is it easier or harder to break your shell apart, for a predator to break your shell apart, if it's got smoother transitions or these squiggly ones that act like teeth holding the shell together, right? It's like if I have my hands like this and you came up to me to yank my fingers apart from each other, that would happen pretty easy. But what happened if I did that? All of a sudden it becomes harder to yank my hands apart. It's harder to break the shell apart if there are more complicated suture patterns between each section of the shell. And so as time goes on, ammonoids developed more and more complicated suture patterns. So that's the big, easy difference to tell them apart. Another one is these sutures are also in a nautiloid going to be concave toward the opening of the shell. Whereas if you look at this, you'll notice that even though there's this kind of concave dip there, it starts off convex towards the opening and it ends convex towards the opening. So they are generally going to be convex towards the opening of the shell. So convex towards the opening, concave towards the opening. And those are the two easiest ways to tell these apart from each other. Okay? We'll talk more about the differences between these when we discuss their occurrence in the fossil record in Module 3. That's what the inside of one of these animals would look like. You've got a variety of different corals. Horn corals, which are very solitary. We also call these rugose corals that kind of look like sad, melty ice cream cones, right? Then you've got tabulate corals. These grow in kind of hexagonal columns, interlocking hexagonal columns. Each one of these columns represents a different colony, and they kind of make bridges with each other as time goes on, and they grow closer together. Scleractinian corals, these are the ones that we have today that make up our coral reefs. They're tiny little organisms that grow calcite exoskeletons and then make colonies with each other. This is what a living coral colony looks like, Scleractinian coral. Sponges have looked very different through time. I say sponge, you think kitchen sponge, right? But this is what ocean sponges look like. They will often form this sort of funnel shape, and they'll work together as in a sort of colony situation where you have this funnel shape, and they are using their tiny little microscopic tendrils to kind of make a wafting motion through the water. They're doing this on the inside of this funnel. And that generates a sort of steady current of water into the funnel. And then they take the water through the sides where the animals are living on the inside of the funnel and kind of flush the water through the pores. And there are specialized cells. So there are the parts of the sponge that are doing this, bring the water in. And then other specialized cells, little animals in there, that pull the plankton and other yummy little things out of the water on its way through the pores. So water goes in the top, gets flushed out the side, minus all the yummy stuff, and the sponge eats the yummy stuff and keeps pulling more stuff in. Okay? These have been around for a very long time, about 600 million years. Bryozoans look very much like corals, some of them. We'll talk more about it later, about how they're different. They're just different animals, even though they form similar structures. Gastropods, so like snails, have been around for a good long time. They developed these sort of curled shell structures. They didn't always have those. Matter of fact, there are gastropods today that don't have those. We call them slugs. Belemnoids are a species of cephalopod, kind of like squid or ammonite or nautiloid, right? These went extinct when the dinosaurs did, but this is what they looked like. They had long, thin, squid-like bodies with one big difference. I think I have them all in the box. They had aragonite spikes in the middle of their bodies, right here. Spikes at the back right there, underneath of their tissues. Want to guess what those spikes were for? This is what they look like, by the way. Those aragonite spikes.
Anchor.
Not to anchor, but right thought. Ballast. Okay? If they wanted to float, they would increase the amount of gas in their bodies and they would float. But if they only had gas, then they would always float. If they want to sink, they need weight to do that. So they release a little bit of gas, and the weight of this spike that they've grown at the back of their bodies brings them down further in the water column. actually how a submarine works too. Okay. And then there's trilobites. We saw these guys earlier. Trilobites have this trilobe body, right? Trilobite. You've got your cephalon is the head, thorax is the body, pygidium is the little butt at the back. Okay, so there's three little sections: the cephalon, thorax, and pygidium. Okay, and look at this guy. He's got a weird fork-looking thing on the front of his face. We still don't know what that was for. It's not like they couldn't joust with each other, right? Some people think that this species would grow those as kind of like a sexual maturity thing, like, hey, I'm ready to mate, right? And then they would just fall off at the end of the mating season. But we have no idea. It's just a weird looking trident thing. But when they're in danger, they actually curl up to protect themselves like this. Much like pill bugs or roly-polies that we've got today. You ever play with these things? Are you okay? I used to love playing with these things as a kid. Living in Hawaii, I'd find a bunch of these and I'd just like poke them until they'd curl up, and then we'd play marbles with them. We would never like squish them or anything. We'd let them go after, but yeah. But they just unroll, and you notice how they've got these interlocking armor plates, and then they just carry along their way. Same thing with a trilobite. Creepy crawlies. Eurypterids. Hope this doesn't give you the creepy crawlies. Very similar, interlocking plates, right? But these would eat trilobites for lunch. These were one of the biggest apex predators for their time. Okay. Matter of fact, they are the largest arthropods that we know about to have existed. Think of these as 7-foot-long underwater sea scorpions. Okay. Yes, glad they're extinct, right? Barnacles. Barnacles, these are the animals that grow on the sides of whales and boats and docks and all of that. You have to scrape them off the side of your ships, or else they weigh your ships down and make them less hydrodynamic. It takes a lot longer to get places. Believe it or not, the closest living relative to these things are crabs. Yeah, I know. Barnacles are actually a kind of crustacean. They diverged a while back from the same ancestor that crabs came from, where crabs developed legs and decided to keep moving. The barnacles decided, you know what, we just want to stay in one place. And so if you ever look at the inside of a crab, they have a surprisingly, they have most of the same body parts of a barnacle. They have most of the same body parts of a crab. They're just using them in this instead of to move around and capture their food by scuttling around and hunting for it. They just let the food come to them, namely plankton and tiny little shrimp and stuff, as this whale in this case is moving around. Insects, also arthropods. This is the largest group in the animal kingdom. Far, far more insects than anything else. Okay. There's a difference between insects and arachnids, by the way. Both are arthropodal, but insects belong to a different group. So calling a spider an insect is actually incorrect. Spiders have 4 pairs of legs. Insects have 3. Insects often have antennae. Spiders have none. So on and so forth. Okay. Plants. We'll talk a lot more about the evolution of plants through time. But for now, let's just say plants started off as water organisms. Okay. Water plants came along before land plants. Okay. Things like algae. Algae developed into something more like this liverwort here, which is a non-vascular plant that can live in moist conditions on land. And from there, we go to vascular plants like ferns. And then from there, we move on into the things that we have more like today, like our trees and our grasses and all of that. Okay. Gymnosperms first showed up about 319 million years ago. Angiosperms showed up about 140 million years ago. So pay special note, you're going to need to know the kingdom, phylum, class stuff that I give you here and the dates for these things for your labs 3 and 4. Grasses didn't show up until about 129 million years ago. Everywhere you see, and even by then, like 129 million years ago, that's when we find evidence of them. But grasslands, like with the prairies we have today, it still took a while to develop. Prior to this, where you see grasses now, there were just a bunch of ferns. There weren't any grasslands, there were fern lands. Okay? So, your assignment, you're going to answer some questions. There's a chart you need to fill in with the dates of these things, or tying the dates of these things to when they show up in the fossil record. And some identification stuff. Any questions about your lab? Take your time on it. Labs 3 and 4, I'm kind of just like, get them done sometime between now and next week. Some of the things you might not get full exposure to until we talk about them in Module 3. Labs 3, 4, and 5, you'll have more context for in Module 3, but I just feel bad putting it off that long because that's 3 labs in a 2-week period. And I don't like doing that to y'all, so I give you Lab 3 now just so you can kind of get a head start on the stuff you can do. Okay? We are going to have our class movie night on May 2nd, by the way. That's the only Friday that's left that really works out for me. So we will meet in that classroom on May 2nd at 6 o'clock and watch movie night. And I will put out a poll so that you all can decide which movie we want to watch for that night. My online students are, of course, welcome to come to that. And you can bring friends, family, whatever. You know the deal. It's the same thing as 1403. But we're watching a movie. The list of movies that I'm going to give you are less natural disaster based. Well, there are a few natural disaster ones. More relevant to the discussions of this class. So there's asteroid impact movies because that's very relevant to this class. But then there's also like Jurassic Park and Ice Age and stuff like that. Okay? Any questions? No? All right. Well, then I will end this here.